This is the story of the most terrifying journey humanity is ever going to take. 4 light-years away, there is a world orbiting the closest star to Earth, a world that may have air, water, and everything our species has ever searched for. But the moment any human being points a ship in that direction, something changes forever. Because what stands between us and that world is not just distance, it is not just better technology or rockets. It is something so extreme and so unforgiving that the scientists who understand it best are the ones who fear it most. Tonight, we are going to take this journey anyway, and by the end, you will understand exactly why reaching Alpha Centauri, our closest neighbor in the universe, may be the most terrifying thing our species could ever attempt. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. Of all the hundreds of billions of stars in our galaxy, one sits closer to us than any other. Astronomers named it Proxima, Latin for nearest. Not a poetic choice, not symbolic, just the simplest, most accurate word they could find for the fire burning at the edge of our cosmic backyard. And it has planets. At least one of them sits inside the zone where liquid water, the one ingredient life as we know it cannot exist without, could theoretically pool on a rocky surface. A world roughly the size of Earth, circling a star just over 4 light-years away. The closest known potentially habitable planet beyond our solar system. Not orbiting some distant sun in a far-off corner of the galaxy. Right here, right next door, in cosmic terms. Here is the problem. 4 light-years, in cosmic terms, is nothing. But in human terms, in terms of time, energy, engineering, and endurance, 4 light-years is so staggeringly, almost insultingly vast that every method of travel humanity has ever built would fail before it even began. The word nearest turns out to be one of the cruelest tricks the universe has ever played on a species that learned to dream about the stars. That tension between so close and utterly unreachable is what this entire journey is about. Before we can understand the distance, we need to understand the destination. And the destination is not a single star, not a dot of light, not one lonely fire burning in the dark. Alpha Centauri is not a single star. It is a family, a triple star system living in the constellation of Centaurus in the far southern sky. 2 of them, called Alpha Centauri A and B, are our Sun's closest known relatives in the entire universe. Alpha Centauri A is a near twin, almost identical in age to our own Sun, slightly larger, radiating the same warm yellow light that has lit our world for 4.5 billion years. Alpha Centauri B is a little smaller, a little cooler, tinted faintly orange, but still recognizably sun-like. These 2 orbit each other like a slow, patient pair of companions circling a shared center of gravity, 1 full revolution every 80 years. At their closest, they pass within roughly the distance between Saturn and our Sun. At their farthest, they drift to about the distance of Pluto. Together, A and B are the 3rd brightest point of light in the entire night sky. In the southern hemisphere, on a clear night, they blaze with a combined brilliance that outshines almost everything else overhead. For most of human history, they looked like a single star, a single brilliant point. And for most of human history, that is exactly what people believed they were. Then there is the 3rd member, smaller, dimmer, much farther out from the pair, orbiting A and B at such an extraordinary distance that a single loop around them takes approximately 550,000 years to complete. At that distance, seen from where A and B stand, this 3rd companion would appear as little more than a faint reddish wanderer in the sky, barely a footnote in the brightness of its siblings. The Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg in 1915, first noticed it a faint star moving through the background sky with exactly the same motion as Alpha Centauri A and B. He confirmed it was gravitationally bound to the system, and he suggested a name, Proxima Centauri. Right now, at this particular moment in the long, slow orbit of all three stars, Proxima has edged slightly closer to us than A and B. The difference is barely a fifth of a light year. In the scale of interstellar space, that margin is almost nothing, but it is enough to give Proxima its title, the closest star to Earth, the nearest sun beyond our own, not by a dramatic measure, just enough. Now here is where we need to slow down, because 4 light years away is a phrase that moves through the mind without landing. We hear it, we nod, we continue. Nothing about it should pass without being felt. A light year is a unit of distance, not time. It is how far light travels in a single year. Light moves at roughly 300,000 kilometers per second, 186,000 miles per second. Fast enough to circle the entire Earth 7.5 times while you blink. At that speed, light crosses from the Moon to Earth in about 1.25 seconds. From the Sun to Earth, 150 million kilometers, or 93 million miles, in about 8 minutes. Now hold that speed constant for a full year, not seconds, not minutes, an entire year, uninterrupted. The distance light covers in that time works out to roughly 9.5 trillion kilometers, about 5.9 trillion miles. Proxima Centauri sits 4.2 of those away from us. Think about what that means in real terms. The light you see from Proxima tonight left that star more than 4 years ago. You are not seeing the star as it is. You are seeing it as it was 4 years before this moment. If Proxima vanished entirely right now, if it simply ceased to exist, you would not know for 4 years and 2 months. The information could not reach you any faster. And if you wanted to send a message toward anyone there, a single word traveling at the fastest speed physics allows, it would take 4 years and 2 months to arrive. Their reply would take another 4. One exchange, over 8 years. This is not a metaphor. This is the speed of the fastest thing in the universe, applied honestly to the nearest possible address. Look at Proxima closely, or try to, and what you find immediately confounds the expectation. The nearest star to Earth is not a blazing sun. Proxima is a red dwarf, far smaller and far cooler than our sun. Its mass is roughly 1/8 of the sun's. If our sun were the size of a basketball, Proxima would be roughly the size of a golf ball. Its surface burns at about half the sun's temperature, giving it a deep, ruddy glow rather than yellow-white light. So faint that even on the clearest night in the darkest sky, the human eye cannot detect it at all. The nearest fire in the sky is completely invisible to us without a telescope. But Proxima is not passive. It erupts, regularly and violently, without warning, blasting out flares of X-ray radiation that bombard anything orbiting close to it, with hundreds of times the radiation that Earth receives from our Sun. During a large flare, that number climbs to 50,000 times. This is not a gentle star. And yet, paradoxically, Proxima is extraordinarily long-lived. Astronomers estimate it will remain stable for another 4 trillion years, roughly 300 times the current age of the universe. Our own Sun, by comparison, has roughly 5 billion years of stable life remaining, meaning Proxima will still be quietly burning long after our star has exhausted its fuel, swelled into a red giant, and erased every trace of the solar system we call home. The nearest fire in the sky is also, in a sense, the most enduring one. And circling that enduring fire, astronomers discovered a planet. They called it Proxima Centauri b, simply taking the star's name and adding the letter B, the way you would number the rooms of a house. The star is the address, the planet is what lives there. The story of how Proxima Centauri b was found begins not with a dramatic announcement, but with years of patient, accumulating suspicion. In 2013, researchers at the European Southern Observatory noticed something small and strange buried in years of data, a tiny rhythmic wobble in Proxima's motion, about 5 kilometers per hour, roughly the speed of a brisk walk, repeating precisely every 11.2 days. But stars are active, they flare, they pulsate. That signal could have been noise. It was not yet convincing enough to declare a world. Careful scientists held back. In January of 2016, an international team led by astronomer Guillaume Anglada-Escudé of Queen Mary University of London launched a dedicated observing campaign called the Pale Red Dot Project. The name was a tribute to Carl Sagan's famous description of Earth as a pale blue dot, a reminder that from Proxima's sky, our sun would appear as nothing more than a faint pinprick of light, pale and distant. For 60 consecutive clear nights, they pointed the HARP spectrograph on the European Southern Observatory's 3.6-meter telescope at La Silla in Chile directly at Proxima. Every clear night, measuring, waiting, watching for that faint walking pace wobble in a star 4 light-years away. The signal was real. On the 24th of August 2016, the team published in the journal Nature a planet with a minimum mass of at least 1.06 times that of Earth. Rocky, almost certainly. Orbiting at about 7.5 million kilometers, 4.6 million miles, from its star. That orbit takes just 11.2 Earth days to complete. So brief that a full year on Proxima b is shorter than 2 weeks here, and sitting precisely within the habitable zone. Anglada-Escudé said afterward, "Searching for the closest potential Earth analogue and succeeding had been the experience of a lifetime. The habitable zone is the range of orbital distances around a star where temperatures might allow liquid water to persist on a planetary surface. At 7.5 million kilometers from Proxima, 20 times closer than Earth is to our Sun, gravity almost certainly locks Proxima b into synchronous rotation. One face permanently turned toward the star, the other permanently turned away. The way our moon always shows us the same side. Not a cycle of day and night, a permanent divide built into the physics of the orbit itself. Some models suggest a thick enough atmosphere could carry heat from the lit side to the dark side, allowing liquid water to persist in a belt along the boundary between light and shadow. But whether Proxima b has an atmosphere at all is completely unknown. Research by NASA's Chandra X-ray Observatory found that Proxima's radiation could strip an unprotected atmosphere in as little as 10 million years. Scientists genuinely disagree on whether life could exist there. Some argue it remains plausible, in sheltered pockets, underground, in water protected from the worst of the radiation. Others argue the flare environment makes surface habitability deeply improbable. Both sides have serious published research behind them. The debate is real. It is not resolved. And then, just as the shape of this system seemed to settle in our minds, the James Webb Space Telescope changed the picture. In August of 2024, Webb's mid-infrared instrument found a faint object near Alpha Centauri A, more than 10,000 times dimmer than the star itself. Possibly a gas giant roughly the mass of Saturn. Then it vanished. Follow-up observations in 2025 found nothing. Researchers called it, with genuine puzzlement, the case of a disappearing planet, their best. Explanation being that the planet had moved behind its star and temporarily out of view. Unconfirmed, but not dismissed. If real, it would be the closest planet ever directly imaged. The nearest star system is not quiet. 3 confirmed planets orbit Proxima. A possible giant world may orbit Alpha Centauri A, and somewhere in that pale red glow there may be a world with liquid water on its surface. So this is the destination, a real world orbiting a real star, 4.2 light-years away. the nearest candidate for life beyond our solar system that we have ever found. Close enough that we know its mass, its orbit, the temperature range its star provides. Distant enough that every instrument we possess cannot yet tell us whether its surface is bare scorched rock or open ocean. To answer that question, we would need to go. And the moment we turn honestly toward that possibility, the moment we stop looking at the destination and start measuring the distance, everything changes. Because 4 light years is not just a number, it is a confrontation with what space actually is, what our machines actually do, and what the laws of physics actually permit. The gap between knowing where something is and being able to reach it is where this entire journey becomes terrifying, and that reckoning begins now. The reckoning begins not with philosophy, but with arithmetic. Humanity has been launching machines into space for nearly 70 years. We have sent spacecraft to every planet in the solar system, and beyond it. We have built rockets powerful enough to drag a fully loaded aircraft off the ground and hurl it into the void. We have walked on the moon, sent probes to Mars, photographed the rings of Saturn, and mapped the surface of Pluto from billions of kilometers away. The machinery exists. The engineering lineage is real. The track record is extraordinary. But here is what that track record cannot do. When we turn it honestly toward 4 light years away, toward that faint, invisible destination we just finished understanding, every craft we have ever built, every speed we have ever achieved, every mission we have ever launched, arrives at the same stark conclusion. Not even close. Begin with the most celebrated spacecraft in human history, Voyager 1. Launched by NASA in September of 1977, the probe spent years studying Jupiter and Saturn before continuing outward in the only direction that remained, away. As of March 2026, nearly 50 years after its launch, Voyager 1 is the most distant human-made object in existence, currently sitting at approximately 25.8 billion kilometers, about 16 billion miles, from Earth. That number sounds immense, and by the scale of anything we have ever physically experienced it is. But now, hold it up against the distance to Proxima Centauri, roughly 40 trillion kilometers, or 25 trillion miles, and the comparison changes character entirely. The greatest distance any human-made object has ever traveled represents less than 0.1% of the distance to the nearest star. Voyager 1 has been flying for half a century. We have barely begun. The probe is genuinely fast, currently traveling at roughly 17 kilometers per second, about 38,000 miles per hour. Voyager 1 covers more than 500 million kilometers every year, fast enough that in a single second it moves further than most people drive in a week. But here is the problem. Even at that speed pointed directly at Proxima Centauri, which it is not, Voyager 1 would take approximately 74,000 years to arrive. Let that number settle, not as a number, but as a span of human time. 74,000 years ago, a supervolcano beneath what is now Lake Toba in Sumatra, Indonesia, erupted in one of the most catastrophic geological events in human prehistory. The eruption was so violent, ejecting somewhere between 2,000 and 3,000 cubic kilometers of material, that it likely plunged the planet into a volcanic winter lasting years, possibly reducing the entire human population to a few tens of thousands of survivors. Our ancestors were hunter-gatherers living in small, scattered bands. Written language would not exist for another 65,000 years. The wheel had not been invented. No city had ever been built. That is when a Voyager-speed spacecraft would have needed to leave Earth in order to arrive at Proxima Centauri today. Not in the time of ancient Rome, not in the Ice Age, 74,000 years ago, before recorded human history by an almost incomprehensible margin. And you might reasonably think, but surely Voyager 1 is not the fastest spacecraft we have ever built. You would be right. On December the 24th, 2024, Christmas Eve, NASA's Parker Solar Probe made its closest ever pass around the Sun, skimming just 6.1 million kilometers, about 3.8 million miles above its surface. At that closest point, the sun's gravity had accelerated the probe to 692,000 kilometers per hour, 430,000 miles per hour, fast enough to circle the entire Earth in under 3.5 minutes. The Guinness World Records confirmed it, the fastest speed ever achieved by any human-made object in history. 3.5 minutes around the Earth. That is genuinely, almost violently fast. But here is what that speed means for a trip to Proxima Centauri, even if the probe could somehow maintain it continuously across 4 light-years of open space, which it cannot, because that speed exists only at the exact moment of closest approach to the Sun, driven by gravity, not engines. Even so, at 430,000 miles per hour, sustained without slowing, the journey to the nearest star would take approximately 6,600 years. 6,600 years. Let that translate into history rather than numbers. 6,600 years ago, writing had not yet been invented, Egypt had not yet had a pharaoh, the wheel had not been conceived, Stonehenge had not been built. Every civilization, every recorded word, every war, every empire, every scientific discovery in the entire span of recorded human history, all of it would fit inside the travel time with centuries to spare. And that is the fastest speed any human machine has ever reached. So we are left with a gap that is not merely large. It is almost insulting in its size. The fastest machines we have ever built would require civilizational timescales to cover a distance the universe considers our backyard. And the very nature of Parker Solar Probe speed reveals a deeper problem. That record was set not by a more powerful engine, but by falling toward the Sun and using its gravity as a slingshot. The probe is not flying to Alpha Centauri. It is circling our own star. In interstellar space, far from the Sun's gravitational pull, there is nothing to slingshot from. A spacecraft moving away from all stars drifts at whatever speed its engines last gave it, and our engines, as we are about to see, are the heart of the problem. So what would make a difference? What fraction of the speed of light would a spacecraft actually need to reach to matter, to complete a journey within a human lifetime? Scientists and engineers have worked this through carefully. To reach Proxima Centauri, 4.2 light-years away, in roughly 40 to 44 years, a spacecraft would need to travel at approximately 10% of the speed of light. That is about 30,000 kilometers per second, 18,000 miles per second, fast enough to circle the entire Earth in barely more than 1 second. In the time it takes a human heart to complete a single beat, such a craft would cover 20,000 kilometers, roughly the distance from London to Sydney and halfway back. Parker Solar Probe, the fastest machine ever built, travels at about 0.06% of the speed of light at its peak. We need 10%. The required speed is roughly 160 times faster than the fastest velocity ever recorded. And that gap is not a gap of engineering ambition. As we are about to see, it is a gap in the fundamental physics of how rockets work. Even 10% of light speed is not comfortable for the humans involved. A 44-year one-way journey to a star no one has yet confirmed is hospitable, in a craft whose engineering must function for half a century without maintenance, driven by propulsion we do not yet possess, followed by a 4-year wait for any signal to return, all of it funded, built and launched by a civilization that may not exist in the same form when the results come back. But before any of that becomes relevant, we first have to answer a simpler, harder question. Why can we not simply build a more powerful rocket and go faster? The answer to that question was worked out in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky, working in the provincial city of Kaluga. Tsiolkovsky had never traveled to space. He had never even flown in an aircraft. He sat in a small house, worked through the mathematics of rocket propulsion, and discovered something that would define the limits of human spaceflight for more than a century to come. A rocket moves by ejecting mass. It burns fuel, forces that burning fuel out of the back of the engine as fast as possible, and the reaction, the equal and opposite push, drives the rocket forward. To go faster, you need more thrust. More thrust means more fuel, but more fuel has more mass, and moving that additional mass to speed requires burning even more fuel, which is also heavy, which requires more fuel still. The fuel requirement does not grow in step with your desired speed. Mathematically, inescapably, it grows exponentially. Picture this. You want to move a single kilogram of cargo to another star at a fraction of the speed of light. You calculate the fuel you need. Then you realize that fuel has mass, so you calculate the fuel you need to move the fuel. Then you calculate the fuel you need to move the fuel's fuel. Each step in that chain multiplies your required mass rather than adding to it. The numbers cascade outward faster than most human intuitions can follow. For a chemical rocket, burning hydrogen and oxygen or similar propellants, there is also a hard physical ceiling on how fast the exhaust can exit the engine. That ceiling is set by the chemistry of the reaction itself at roughly 4 to 5 kilometers per second. You cannot increase it by spending more money or designing a more elegant nozzle. The molecules do not care about ambition. That ceiling is written into them. Caleb Scharf, a NASA astrobiologist and researcher who teaches at Columbia University, calculated what the rocket equation demands for a 100-year mission to Alpha Centauri using chemical propulsion. He found that the amount of fuel required would exceed 10 to the power of 2,200 times the mass of the entire observable universe. Not 10 times, not 10 billion times, 10 raised to the 2,200th power times. The observable universe contains roughly 2 trillion galaxies. Multiply everything in it by itself more than 2,000 times over, and you approach, only approach, the fuel requirement for a chemical rocket to Alpha Centauri in 100 years. Chemical rockets did not fall short of the stars because we have not built them large enough. The rocket equation itself forbids it. The physics closes the door. So here is what we have established honestly. The nearest star with a potentially habitable planet sits 4 light-years away. Our fastest probes need thousands of years to cover that distance even at their peak. To make the journey in any remotely human time frame, we need a speed roughly 160 times greater than the fastest velocity any machine has ever reached. And the propulsion method that carried us to the Moon, to Mars, to the edge of the solar system, the combustion of chemical fuel, cannot reach that speed even in principle. The mathematics does not allow it, not with improvements, not with any amount of engineering refinement. For the first time in human technological history, we are facing a category of problem that our most trusted method of solving problems, build a bigger engine, add more power, does not touch. The challenge is not how to build a better rocket. The challenge is how to abandon the concept of a rocket entirely and think about propulsion from the ground up, using physics rather than chemistry to generate movement. And here is where the story turns unexpectedly. Because when physicists and engineers began asking not, how do we improve chemical rockets, but what does physics actually permit when chemistry is no longer the constraint, the answers that came back were not empty. They were strange. They were technically brutal in their requirements, but they were not nothing. Some of the most serious scientific institutions in the world, from NASA to Harvard to the European Space Agency, have spent real resources exploring real propulsion concepts that do not rely on burning anything at all. Concepts driven by light itself, by nuclear fire, by the physics of antimatter. And at the far end of that spectrum, one proposal that sounds almost impossible has received more than $100 million in funding and the public endorsement of Stephen Hawking. What it would take to send even a small probe to Proxima Centauri, genuinely within a human lifetime, is now an active scientific and engineering question, not a fantasy. The ideas are real, the problems are real, and both are more extraordinary than almost anyone outside the field expects. The ideas are real, but before any of them can be understood, before we can honestly evaluate which ones might work and which ones cannot, we first have to confront the wall they all run into. A wall that is not made of engineering or funding or political will. A wall made of physics itself. A wall that has a name: the speed of light. Light travels at roughly 300,000 kilometers per second, about 186,000 miles per second. In 1 second, a beam of light could circle the entire Earth 7.5 times. Every proposal for interstellar travel, every concept, every design, every dream must be understood in relation to that number, because it is not just fast. According to Albert Einstein's special theory of relativity, published in 1905 and verified by every experiment ever conducted to test it, the speed of light is also the absolute ceiling, the hard limit of the universe. Nothing with mass, no spacecraft, no particle, no person can reach it. Not because we lack the technology, because the physics does not permit it. To understand why that ceiling exists, consider what happens to energy as speed increases. At everyday speeds, a car, a rocket, even the Parker Solar Probe at its fastest, the energy required to accelerate an object grows in a straightforward way. Double your speed, roughly quadruple your energy. Manageable. But as you approach the speed of light, the relationship between speed and energy changes character entirely. The energy required stops growing proportionally and begins growing toward infinity, not very steeply, infinitely. At 90% of light speed, an object requires 2.3 times its rest energy just to exist at that speed. At 99%, it requires 7 times its rest energy. At 99.9%, 22 times. The closer you push toward the limit, the more energy each additional fraction of a percent costs, and the costs keep growing without end. Reaching the speed of light exactly would require infinite energy, not enormous energy, infinite. For an object with any mass at all, the speed of light is unreachable, not as a practical matter, but as a mathematical certainty. The universe appears to have placed a hard ceiling, and it has placed it exactly where the most useful speed would be. What this means for interstellar travel is this: we cannot travel at the speed of light. We can only travel at some fraction of it, and the higher that fraction, the more catastrophically expensive the energy bill becomes. Every propulsion concept humanity has ever seriously considered is, in reality, a negotiation with that wall, trying to get as close to it as possible with the energy and technology available, while accepting the hard reality that the wall itself will never be reached. The question is, how close can we get? The first serious step beyond chemical propulsion was the ion engine, and it represents a genuinely elegant shift in thinking. A chemical rocket works by burning fuel. An ion engine works by electricity. The engine takes a gas, typically xenon, a dense, chemically inert element that stores easily under pressure, and strips electrons from its atoms, creating ions. Ions are atoms with an electrical charge. Charged particles can be accelerated by electric fields with great precision. The engine fires those accelerated ions out the back at speeds of 20 to 50 kilometers per second. That's 12 to 30 miles per second, compared to the 4 to 5 kilometers per second maximum of the best chemical exhaust, more than 10 times as fast. And because the kinetic energy of an exhaust jet increases with the square of its speed, that improvement in exhaust velocity translates into dramatically better fuel efficiency. How much better? NASA's Dawn spacecraft, which used ion propulsion to orbit both the asteroid Vesta and the dwarf planet Ceres, making it the first spacecraft ever to orbit 2 separate extraterrestrial bodies, consumed roughly 425 kilograms of xenon over its entire mission. 425 kilograms of xenon achieved what would have required more than 4,000 kilograms of conventional propellant for the same mission. The engine squeezed 10 times the performance out of the same amount of fuel. But here is what an ion engine feels like from the inside. At full throttle, Dawn's engines produced about 91 millinewtons of thrust. That is the force you feel when you lay 2 sheets of notebook paper on your open hand. 91 millinewtons. The engine is so gentle, so feather-light in its push, that to go from a complete stop to 60 miles per hour, 100 kilometers per hour, would take 4 full days of continuous firing. 4 days. 0 to 60 miles per hour. And that patience is precisely the point. An ion engine cannot get out of a parking lot quickly, but it never stops. It fires and fires and fires, building velocity imperceptibly day after day, week after week for years. Dawn's engines fired for a cumulative total of roughly 2,000 days across its mission, more than 5.5 years of continuous thrusting. The gentle persistence added up to a total velocity change across the mission equivalent to what the Delta II rocket needed to launch the spacecraft in the first place. A feather push, applied long enough, becomes something remarkable. But for interstellar travel, even this remarkable efficiency falls short. Ion engines are powered by electricity, which in the inner solar system comes from solar panels. As a spacecraft moves away from the Sun, solar power diminishes rapidly. Ion engines are superb for solar system exploration. For 4 light years across open interstellar space, they cannot generate sufficient energy to matter. Ion propulsion is not the answer to the stars, but it opened a door in our thinking. If chemistry is the ceiling, what burns hotter than chemistry? The answer physicists arrived at in the 1950s was, by any measure, one of the most audacious engineering proposals in human history. In 1958, at a company called General Atomics in San Diego, a team led by physicist Ted Taylor and the brilliant mathematician Freeman Dyson began serious work on a spacecraft propelled by nuclear explosions. The project was called Orion. The concept was almost brutally direct: detonate a small nuclear bomb behind a massive steel pusher plate at the rear of the spacecraft. The explosion converts a propellant surrounding the bomb, typically water or a dense polymer, into a superheated plasma that slams into the plate and drives the craft forward. Absorb the shock with a system of enormous spring-loaded shock absorbers. Detonate another bomb. And again. And again. 1 bomb per second, for as long as the mission requires. The idea sounds violent, to the point of absurdity. But Dyson and Taylor were not dreamers without credentials. Their calculations were meticulous. The designs were physically feasible with technology that existed in 1958. A successful model test, conducted in November of 1959, physically demonstrated the concept using sequenced chemical explosions. A small craft, driven upward by one explosion after another, performing exactly as predicted. Orion's potential performance was extraordinary. Fission-powered versions could theoretically reach 3 to 5% of the speed of light. A fusion-enhanced design, which Dyson explored in detail in a 1968 paper published in Physics Today, could reach 8 to 10%, fast enough to bring the travel time to Alpha Centauri down from tens of thousands of years to just over 4 decades. But Orion was cancelled in 1964. Not because the engineering failed, not because the physics was wrong. The project died because the United States signed the Partial Nuclear Test Ban Treaty in 1963, which prohibited nuclear explosions in the atmosphere and in space. The politics of the Cold War, not the laws of physics, ended the most technically credible path to the stars that had ever been seriously designed. Freeman Dyson, who spent the rest of his long life grieving that decision, described Orion as the vehicle that could have made humanity a spacefaring civilization in the 1970s. We will never know if he was right. The design sits in the archives, complete, coherent, and permanently grounded. Beyond nuclear fission lies nuclear fusion, the process that powers the Sun. Fusion occurs when 2 light atomic nuclei are forced together under extreme pressure and temperature, merging into a heavier nucleus and releasing an enormous amount of energy. gram for gram, fusion fuel releases roughly 5 to 10 times more energy than fission, and without the heavy, radioactive waste products. In the 1970s, a team of scientists and engineers at the British Interplanetary Society spent 5 years designing an interstellar probe based on fusion propulsion. The project was called Daedalus, named for the mythical craftsman who built wings of feathers and wax. The design called for a 2-stage fusion rocket, burning pellets of deuterium and helium. 3 fuel ignited by electron beams at a rate of 250 times per second. The ship was unmanned, enormous, roughly 5 times the length of a football field, and theoretically capable of reaching 12% of the speed of light. At that speed, it would arrive at Barnard's star, a red dwarf 6 light-years away, in approximately 50 years. The Daedalus study ran to hundreds of pages of detailed engineering. The physics worked. The numbers were internally consistent. On paper, a fusion rocket could genuinely reach the stars within a human lifetime. But here is the problem. Every fusion drive design in history, Daedalus, and the more recent concepts that followed it, depends on something humanity has never actually built: a sustained, net-positive fusion reactor. After decades of research and billions of dollars of investment, scientists have recently achieved fusion reactions that produce more energy than the laser energy delivered to trigger them, a major milestone reached by the National Ignition Facility at Lawrence Livermore National Laboratory in 2022. But converting that laboratory milestone into a functioning drive system capable of propelling a spacecraft across light years remains a formidable engineering challenge of its own. Fusion propulsion remains the most credible path to genuine interstellar speeds for a crewed mission, but it also remains dependent on technology that does not yet exist in operational form. The physics is real, the engineering is still ahead of us, and then there is antimatter, the concept that takes every other energy comparison and renders it irrelevant. Antimatter is the mirror image of ordinary matter. Every particle of normal matter has an antimatter counterpart, identical in mass, but opposite in charge. When matter and antimatter meet, they do not chemically react, they annihilate. Both particles are completely converted into pure energy with 100% efficiency. Nothing is wasted, no byproduct remains, just energy, released with perfect completeness. The energy density of matter-antimatter annihilation is staggering. Kilogram for kilogram, it releases roughly 10 billion times more energy than the hydrogen-oxygen combustion that powers conventional rocket engines, and about 300 times more than the fusion reactions at the Sun's core. Theoretically, a matter-antimatter drive could propel a spacecraft to 40% of the speed of light, fast enough to reach Proxima Centauri in roughly 10 years. So why are we not building one? Because antimatter is effectively the rarest and most expensive substance in human experience. All of the antiprotons that CERN, the world's most powerful particle physics laboratory, produces in an entire year, using the most advanced accelerators ever built, would be enough to light a 100-watt electric bulb for 3 seconds. 3 seconds. A mission to Alpha Centauri would need, based on current estimates, several grams to several kilograms of antimatter. At current production rates and costs, generating even a single gram would cost approximately $4 million in electricity alone, and require production infrastructure that simply does not yet exist. Storing it is equally challenging. Antimatter cannot touch any ordinary container without annihilating on contact. Scientists have managed to trap only small numbers of individual antihydrogen atoms for brief periods. The leap from trapping a few atoms to storing the kilograms required for an interstellar drive is almost incomprehensible. Antimatter propulsion may be the most powerful idea in the history of spaceflight, and it may remain, for now, exactly an idea. But here is where a completely different kind of thinking enters the conversation. An idea that sidesteps the fuel problem entirely, because it carries no fuel at all. On April the 12th, 2016, the 55th anniversary of Yuri Gagarin's first spaceflight, the physicist and entrepreneur Yuri Milner stood alongside Stephen Hawking in New York City and announced one of the most extraordinary scientific proposals of the century. The project was called Breakthrough Starshot. The initial funding was $100 million. The advisory board included Harvard's Avi Loeb as chairman, physicist, and former NASA Ames director, Pete Worden as executive director, and some of the sharpest minds in astrophysics and aerospace engineering. And the proposal itself was this: don't send a large ship, send thousands of tiny ones each, barely the size of a postage stamp, gram-scale probes called star chips, carrying miniaturized cameras, sensors, and a communication system attached to a gossamer sail roughly 4 meters square and only a few hundred nanometers thick, thinner than a human cell. The sail is the engine, not a chemical engine, not a nuclear one. The engine is light itself, a massive array of ground-based lasers with a combined output of up to 100 gigawatts, roughly the power output of 100 large nuclear power plants, focused into a single coherent beam, would be directed at each star chip as it ascended above Earth's atmosphere. For approximately 10 minutes, that beam would push on the sail with the pressure of light itself. The photons reflecting off the sail would transfer momentum to it, gradually, then explosively. Over those 10 minutes, the sail would accelerate to roughly 20% of the speed of light, 60,000 kilometers per second, or about 37,000 miles per second. At that speed, a signal traveling from New York to London, 5,500 kilometers, would arrive in less than 1/10,000th of a second. A journey to Proxima Centauri, 4.2 light-years away, would take approximately 21 years. 21 years, not 74,000, not 6,000, 21. The signal sent back from the closest approach to the system, traveling at the speed of light, would take 4 more years to arrive. Scientists who launched the mission in their 30s could, in their late 50s, receive the first images of Proxima Centauri's planetary system directly, possibly including Proxima b. The idea is physically legitimate. Laser propulsion is real physics. Photons carry momentum, and reflected photons transfer that momentum to whatever surface they strike. Caltech researchers took the first experimental steps in early 2025, building a test platform to directly measure radiation pressure on ultra-thin sail membranes, moving from theoretical design to actual laboratory measurement. But the engineering challenges are enormous and real. The laser array itself would be roughly 3 kilometers in diameter. Keeping a coherent 100-gigawatt beam focused precisely on a 4-meter sail, traveling at 20% of light speed, requires optical systems of unprecedented precision. The sail must be reflective enough to avoid being vaporized by the beam, thin enough to be accelerated effectively, and structurally stable enough to survive the acceleration. Communications from 21 light-years away, from a postage stamp-sized probe, would be vanishingly faint. And as of September 2025, the project has been placed on hold indefinitely, having spent only a fraction of its initial funding, according to project researchers, while foundational challenges remain unsolved. Breakthrough Starshot is not dead, but it is waiting for breakthroughs that have not yet arrived, and even the most optimistic scenario, a probe at 20% of light speed, confronts a further problem that all these concepts share, a problem that only becomes relevant at the speeds we are discussing. At 20% of light speed, an interstellar medium that is otherwise effectively empty becomes a hazard. The space between stars is not a perfect vacuum. It contains hydrogen atoms at extremely low densities, roughly 1 atom per cubic centimeter, and traces of dust. At 20% of light speed, each hydrogen atom encountered by the probe carries the impact energy of a particle in a high-powered physics experiment. Over a journey of 4 light-years, even the sparse interstellar medium delivers a cumulative bombardment that would strip away surface materials, erode sensors, and degrade any unshielded electronics. The faster the probe travels, the more violent this effect becomes. At 20% of light speed, the engineering challenge is significant but potentially manageable. At 50, at 60, at 80%, the interstellar medium becomes genuinely destructive. Speed gains beyond a certain point may not be survivable for any hardware we know how to build. And that is before considering the relativistic effects that begin to transform the experience of time itself at high fractions of light speed. Effects that matter enormously if the question is not just whether a probe reaches the destination, but whether a human being could survive the journey and what they would return to. So here is the picture of what physics actually offers: a ladder of propulsion concepts, each more powerful and more difficult than the last. Ion engines, 10 times better than chemistry, but still hopelessly slow for stars. Nuclear pulse, theoretically capable, politically extinguished. Fusion, promising enough that serious scientists designed a complete ship, but dependent on technology still being developed. Antimatter, theoretically the most powerful energy source known, practically unavailable at any meaningful scale. And at the extreme end, a light sail driven by a laser, requiring no fuel at all, physically real, already funded at the proof-of-concept stage, temporarily on hold, and capable of reaching Proxima Centauri in 21 years. But only a probe, barely a gram, because here is the question that none of the propulsion concepts so far have been asked to answer. Not for a chip, not for a camera, for a person, a human body with its need for air, for food, for water, for space, for light, for other human beings, for time that has meaning, for everything that makes a 70 or 80-year life a life rather than merely a duration. What would it actually take to send not a gram, but a civilization across 4 light years of empty space? What would those people eat? What would they do? Who would they become? And when they finally arrived, if they did, would any part of them still recognize the home they left behind? A probe weighing 1 gram asks almost nothing of us. A sail the size of a bedroom. A chip smaller than a fingernail. The engineering is brutal, but the question of what it carries is simple. Instruments. Data. The cold calculation of cameras pointed at a distant world. But a person asks everything. A person needs air, roughly half a kilogram of oxygen every day, consumed and exhaled and consumed again in a cycle that must never break. A person needs water, food, warmth, light, sleep, and the company of other people in quantities that science cannot fully substitute or reduce. A person needs meaning, a reason to wake up, a sense of purpose, some thread connecting today to tomorrow that does not simply read, "We are still crossing the void." A person ages, grieves, loves, argues, breaks down, heals, and eventually dies. And if the journey takes longer than 1 lifetime, as most serious estimates of a crewed interstellar mission suggest it would, then everything that person is, and everything they pass to their children, and everything those children become, must all happen inside a hull travelling through the emptiest environment in the known universe, with no possibility of turning back. This is the dimension of interstellar travel that no propulsion concept in the known history of engineering has ever been asked to answer. Not the thrust, not the fuel, the humanity. The concept of a multi-generational ship, what engineers and theorists sometimes call a generation ship, a world ship, or an interstellar arc, is straightforward in principle and staggering in implication. The idea is this: rather than solving the propulsion problem well enough to make the journey in a single lifetime, you design a ship that sustains entire communities for however long the journey takes. The original crew sets out, grows old, and dies during the voyage. Their children continue, their children's children continue. Generations are born, live their entire lives, and die. Inside the hull, never having seen Earth, never having seen the destination, existing entirely in the hyphen between departure and arrival. The people who finally step out at Alpha Centauri, if the mission succeeds, may share almost nothing with the people who climbed aboard except a last name and a story. The first person to write seriously about this idea was Robert Goddard, the same American engineer who became one of the founders of modern rocketry, in a private essay written in 1918 titled The Ultimate Migration. He described a ship carrying sleeping passengers across interstellar space, awakening them at the destination. But the multi-generational variant, where people do not sleep but live, fully and completely across multiple generations, raises problems that sleep neatly sidesteps, problems that have occupied biologists, psychologists, anthropologists, and ethicists ever since. Start with the most basic requirement: air. Right now, wherever you are, your lungs are pulling oxygen from the room around you, extracting roughly 21% of the air with each breath, and exhaling carbon dioxide in return. The air in this room will be refreshed by ventilation, by open windows, by the vast reservoir of Earth's atmosphere pressing against every surface. On a ship between the stars, none of that exists. Every molecule of oxygen must be produced on board. Every molecule of carbon dioxide must be captured and recycled. Nothing can be wasted, nothing can leak, and nothing can fail. Not for a day, not for a year, not for a century. This is not a mechanical engineering problem with a clever solution. This is a living systems problem, and the consensus among the scientists who study it is that the only viable long-term solution is biology itself, a closed ecosystem running aboard the ship in which plants and microorganisms continuously produce oxygen, purify water, absorb carbon dioxide, and grow food in a cycle that mirrors, as closely as possible, the biosphere of the planet the crew left behind. Picture a farming deck, rows of crops under artificial lighting, drawing nutrients from recycled water and waste, cycling carbon through photosynthesis, releasing oxygen into the ship's atmosphere. Not a decorative addition to the craft. The lungs of the ship. Without it, the crew dies. With it, the crew must tend it, protect it from disease, maintain its lighting systems, its water chemistry, its temperature, every hour of every day, for however long the voyage lasts. And that is only the beginning of the inventory. Clean water requires continuous recycling from urine, humidity, washing, and every other source of liquid. Food requires not just farming, but preservation, preparation, nutritional completeness across every age group and health condition that will arise over decades. Medicine requires a fully equipped facility for childbirth, surgery, chronic illness, and everything else that happens to a population over generations, staffed by people trained aboard, using equipment that must be repaired from within. The ship is not a vehicle. The ship is a world. And now, here is where the challenge becomes genuinely staggering, because here is the question that reveals just how large that world must be. How many people does it take? The intuitive answer is, as few as possible. The fewer the people, the smaller the ship, the simpler the life support, the lighter the fuel requirement. 100 people might seem sufficient. Some early proposals suggested numbers as low as 150. But here is the problem. Scientists who study population genetics, the biology of how genetic traits survive, degrade, or change across generations, have found that small populations are extraordinarily fragile. A founding population that is too small faces what geneticists call inbreeding. When a small group of closely related people reproduce across generations without access to new genetic material from outside, harmful recessive traits accumulate. Genetic diversity, the biological insurance policy that allows a population to survive new diseases, new environments, and unexpected stresses, erodes, not in one generation. Gradually, the way a thread frays over time until the fabric tears. In 2014, Dr. Cameron Smith of Portland State University published a detailed analysis in the journal Acta Astronautica, one of the foremost peer-reviewed journals in space science, examining what a genetically viable population for multi-generational interstellar travel would actually require. His conclusion shattered the earlier comfortable estimates. Smith found that an effective population of at least 10,000 people would be needed to maintain good genetic health over multiple generations. To account for natural disasters, disease, accidents, and the unpredictable pressures of confined living, he recommended an initial crew closer to 40,000. 40,000 people. That is not a crew. That is a city. A city that must be fed, housed, medically supported, educationally served, psychologically sustained, and politically governed, in a sealed hull traveling through interstellar space with no possibility of resupply, no possibility of rescue, and no possibility of anyone leaving. Other researchers have proposed smaller numbers with genetic supplementation, frozen embryos and genetic material stored in cryogenic banks to maintain diversity without requiring a large initial population. French astronomer Dr. Frédéric Marin and colleagues at the Astronomical Observatory of Strasbourg created a sophisticated computer simulation called Heritage specifically to model generation ship populations, finding that combined with cryogenic genetic banks, smaller crews might function. But the scientific debate is genuine and unresolved. What number is sufficient is not yet agreed upon. What is agreed upon is this: the early estimates of a few hundred people were almost certainly wrong, but even accepting for the moment a crew large enough to survive genetically, what does the psychological reality of that journey look like? We have data, not from stars, but from simulations. Between 2010 and 2011, Russia's Institute of Biomedical Problems in Moscow, working jointly with the European Space Agency and China's space program, conducted the Mars 500 project, the longest and most rigorous Earth-based simulation of an interplanetary mission ever attempted. 6 carefully selected male volunteers, engineers, physicians, military professionals, were sealed inside a mock spacecraft for 520 consecutive days. That is 17 months. Not space, but sealed away from the outside world with a 20-minute communication delay to simulate the reality of a Mars mission, with no way out until the experiment concluded. The researchers who analysed the data found something important. 4 of the 6 crew members experienced significant disruptions to their sleep patterns over the course of the mission. 2 developed persistent problems, one with chronic sleep deprivation, altered alertness, and elevated stress markers that persisted throughout. 2 crew members with the highest measured stress and exhaustion were responsible for 85% of all recorded interpersonal conflicts during the mission. And this was just 17 months. 6 people. On Earth, where family was a telephone call away, where the door could theoretically be opened. Now extend that to decades or centuries. Imagine the same psychological pressures, the monotony, the confinement, the inescapable proximity to the same faces day after day, compounded not over 17 months but over entire lifetimes, over generations in which every person aboard has always known only the same corridors, the same faces, the same recycled air, the same manufactured light, no seasons, no wild places, no cities to walk through, no strangers to encounter, only the hull and the people inside it and the void pressing against every surface from outside. Psychological researchers studying isolation in extreme environments, Antarctic expeditions, submarine crews, polar stations, have documented a consistent pattern they call the third quarter phenomenon. The middle of a long mission, once the novelty has worn off and the end is not yet visibly approaching, is typically the most psychologically dangerous period. Mood drops, conflict rises, motivation hollows out, sense of purpose becomes difficult to sustain. In a mission lasting a human lifetime, that third quarter might last decades. A ship carrying thousands of people across generations is not just a life support problem, It is a civilization problem. Who makes decisions about resource allocation, about food distribution, medical priority, living space, reproductive rights? Who settles disputes, and what gives them that authority? What happens when those in power abuse it? What mechanisms exist for removing a leader, challenging a law, or protecting the rights of individuals when there is nowhere else to go and no court beyond the hull? Ethicists and social scientists who take the generation ship seriously have concluded that the ship would need to replicate, in miniature, the full architecture of a functioning society. Hospitals, schools, some form of governance, perhaps elected, perhaps hereditary, perhaps structured around expertise, a security function, some framework of law that applies to everyone and cannot be escaped, a judiciary. All of this compressed into a structure where every person knows every other person, where privacy is constrained by space, and where the same social tensions that have driven revolutions and civil wars on Earth, inequality, resentment, fear, the hunger for control, would all exist, unescapable, in a sealed environment. And here is the structural paradox that no one has solved. The mission requires every generation to maintain the ship, serve its functions, and commit to the destination. But subsequent generations never agreed to go. They were born into it. Every child born on that vessel arrives in a world not of their choosing, with a mission assigned to them before they could speak. Their parents chose this. Their grandparents chose this. They did not. And yet the ship cannot function without them. The crops must be tended. The engines must be maintained. The destination must still matter to people who have never seen Earth and cannot see Alpha Centauri. Serious ethicists have openly questioned whether launching a generation ship is morally justifiable at all, precisely because of the generations who have no say. The question is genuine, documented, and unresolved. Some argue that the mission gives those generations a purpose and a community. Others argue that confining people to a mission they never chose in a world they cannot leave is a profound violation of autonomy, regardless of the nobility of the goal. And then there is the question of what it means to grow up entirely inside a hull. Think about how much of human identity is shaped by the experience of being outside, by weather, rain on your face, wind, the particular quality of light at different hours of the day and different times of year, by landscape, open space, distance, the sense of a horizon that extends beyond what you can see, by diversity, strangers, cities, different languages and foods and customs encountered outside your immediate community, by impermanence, the knowledge that your surroundings can change, that you can leave a place, that the world is larger than your current view of it. Children born on a generation ship have none of that. Their sky is a ceiling, their weather is air recycling, their horizon is the end of the corridor. Every face they will ever know for their entire lives is already on the ship. Their world has an edge, and everyone knows where it is. The psychological development of human beings under those conditions is genuinely unknown. No study has ever subjected a child to multi-decade confinement and measured the results. What we do know, from research on children raised in severely restricted environments, is that the effects of sensory limitation, social restriction, and reduced autonomy on developing minds can be significant and lasting. Whether carefully designed environments, green spaces, varied social interaction, maintained art and culture and education could compensate for the absence of everything a planetary childhood contains is not yet something any scientist can honestly answer with certainty. And as the generations accumulate, the identity question deepens. The first crew members leaving Earth carry Earth inside them. They remember its oceans and its gravity. They grieve it perhaps. They speak of it to their children in the way that immigrants speak of a home left behind, with love and loss and the specific ache of irreversibility. Their children grow up hearing those stories. Earth is real to them, even if distant, a place their parents knew, a place they can imagine. But their children's children hear those same stories secondhand. And the generation after that hears them third-hand. Each transmission becomes more abstract, more mythologized, less felt. At some point, Earth becomes not a memory, but a legend. Not a home, but a founding story. Something like what ancient migrations are to us, intellectually known, emotionally unreal. Would those people arriving at Alpha Centauri after a century or more of voyage still feel they were completing a human mission? Or would they feel, entirely justifiably, that they were completing someone else's mission, a mission designed by people long dead for reasons that made sense to a world they have never seen? So here is what a crewed interstellar mission actually requires. Not a ship with a crew, a self-sustaining civilization carried in a sealed hull for however long the journey takes, capable of maintaining its physical systems, its genetic health, its psychological cohesion, its social structures, and its purpose across multiple generations of people who did not all choose to be there. Cameron Smith, whose genetic research shaped how scientists now think about crew size, said something that captures the full weight of this challenge. He described a generation ship not as a vehicle, but as a portable biosphere, an entire ecological, social, and cultural system engineered to sustain and reproduce itself independent of any planet. That is not a spacecraft. That is a civilization that decided to leave. And even accepting all of that, the closed ecosystems, the minimum viable population of tens of thousands, the governance structures, the psychological architecture, the ethics of raising children inside a mission they never chose. Even accepting every one of those challenges as solvable, there is still a layer of the journey that has not yet been addressed. A layer that exists not in the hull, but outside it. Because the space between stars is not merely empty. At the speeds required for any mission even approaching human timescale, the void itself becomes an adversary. Cosmic radiation streaming constantly from every direction at energies that ordinary shielding can only partially deflect. Microscopic dust particles that strike like bullets at relativistic speeds. And at the far end of the speed spectrum, something even stranger, the physics of time itself begins to behave differently. The faster you move, the slower your clock ticks compared to the world you left. A journey that feels like decades to those aboard might correspond to a different span of time for everyone left on Earth. This is not science fiction. This is one of the most precisely verified predictions in all of physics, and its implications for an interstellar mission, for the people inside the hull and for the civilization they leave behind, are among the most profound and disorienting consequences of everything we have covered so far. The void between stars is not what it looks like from a photograph. In photographs, interstellar space appears as pure darkness, absolute, total, and empty, a black backdrop against which stars burn. But that apparent emptiness is an illusion created by the limits of human vision. The space between the stars is in fact a physical environment, a dilute medium of gas and dust particles and high-energy radiation that streams constantly in every direction. At the walking pace of a generation ship, or even at a significant fraction of the speed of light, most of that environment is manageable. But at the speeds any mission to Alpha Centauri would require, speeds that begin to approach a meaningful fraction of light speed, the void transforms. What was a negligible background becomes a relentless physical assault on every material and biological system inside the hull. The threats are real, verified, and deeply studied, and understanding them is part of understanding what a journey to the nearest star would truly cost. Start with the space itself. The interstellar medium, the material that fills the space between the stars, is not a vacuum in the perfect sense. On average, Roughly one hydrogen atom occupies every cubic centimetre of interstellar space. One atom per cubic centimetre sounds impossibly sparse. To put it in familiar terms, the best vacuum a laboratory on Earth can produce typically contains billions of atoms per cubic centimetre. The space between the stars is billions of times emptier than our most sophisticated artificial vacuum. Any container we have ever built still holds an enormous number of molecules compared to interstellar space. And yet, that single atom per cubic centimetre adds up. A spacecraft travelling to Proxima Centauri, 4.2 light-years away, would sweep through an enormous volume of space on its journey. Researchers at Harvard University who studied this problem calculated that a probe with just 1 square centimetre of frontal area would encounter approximately 2 million trillion atoms on the full journey to Proxima. That is, roughly speaking, the number of atoms in a single grain of salt. Spread over 4 years of travel, a grain of salt's worth of impacts sounds harmless, but the speed at which those impacts happen changes everything. Mixed into that dilute gas are also grains of cosmic dust, particles of silicate and carbon compounds, remnants of ancient stellar processes, ranging in size from clusters of a few molecules to particles roughly the width of a human hair. At everyday speeds, these grains are negligible. At the velocities required to reach another star in any human-relevant timeframe, they are not. Before the speed problem even becomes relevant, any crew venturing into the open space between the stars faces the first and most persistent threat: galactic cosmic rays. NASA has formally identified cosmic radiation as the #1 health risk for astronauts travelling beyond low Earth orbit. Not the cold, not the vacuum, the radiation. And for good reason. Galactic cosmic rays are not the gentle radiation you might associate with X-rays or sunlight. They are atomic nuclei, the cores of atoms from hydrogen all the way up to iron and beyond, stripped of their surrounding electrons by the violence of distant supernova explosions and accelerated to nearly the speed of light over thousands of years. They stream through interstellar space in all directions, continuously, at close to the maximum speed the universe permits, and they carry enough energy that no material shield can stop them with perfect efficiency. On Earth, 2 layers of defense protect us from most of this radiation. The planet's magnetic field deflects charged particles before they reach the atmosphere. The atmosphere itself absorbs what gets through. An astronaut in low Earth orbit aboard the International Space Station still receives considerable protection from the lower portions of Earth's magnetic field. Even so, ISS astronauts accumulate more than half a millisievert of radiation exposure every single day, the equivalent of roughly 5 chest X-rays, daily, sustained for the duration of their mission. In just 12 days aboard the ISS, an astronaut receives the same annual radiation dose that a commercial airline crew member receives from their elevated altitude exposure over a full year. In deep interstellar space, far from any planetary magnetic field, the full flux of galactic cosmic rays arrives from every direction, continuously. And here is the disturbing complication that NASA and physicists have identified. For the most energetic galactic cosmic rays, adding shielding can actually make the problem worse. High-energy cosmic ray particles slam into shielding material and generate a shower of secondary radiation, a cascade of different particle types, some of which are more biologically damaging than the original incoming particle. Thin shielding is often harmful rather than helpful for these particles. Thick enough shielding would work, but the mass required defeats the purpose of building a spacecraft at all. The biological consequences of long-term deep space radiation exposure include elevated lifetime cancer risk, damage to the central nervous system, cognitive changes, memory degradation, cataracts, cardiovascular damage, and in extreme cases, acute radiation syndrome. NASA's own career radiation limits apply only to missions in low Earth orbit. Guidelines for deep space missions do not yet officially exist, because the risk is not yet well enough understood to quantify confidently. A crew aboard a generation ship crossing 4 light-years would be living inside this radiation environment not for months but for their entire lives, across multiple generations. Now add the velocity problem. At slow speeds, the dust and gas of the interstellar medium are negligible. Even at the speed of our fastest probes, particles of cosmic dust do not have enough relative velocity to cause significant damage. But as speed increases toward a fraction of light speed, the physics of impact changes character entirely. The kinetic energy of a collision scales with the square of the relative velocity. Double your speed, and each impact carries 4 times the energy. At 20% of light speed, the target velocity for breakthrough starshot, those atoms and dust grains the probe encounters are not drifting into it at casual speed. From the probe's perspective, each particle is flying toward it at 60 million meters per second. 60 million meters per second. In that same second, a typical commercial aircraft covers roughly 250 meters. The interstellar atoms are approaching 240,000 times faster. In a detailed study published by Thiem Hoang and colleagues at the University of Toronto, working as part of the Breakthrough Starshot research team, scientists calculated the cumulative damage that interstellar gas and dust would inflict on a probe traveling to Proxima Centauri at 20% of light speed. A typical dust grain, just 1/10 of a micron across, a particle far too small to see and far too small to feel, hitting at that speed carries enough energy to cause what physicists call explosive evaporation. The material at the impact site instantly vaporizes. The surrounding surface melts. The damage track extends into the structure of the material. Over the full journey to Proxima, dust bombardment alone would erode a surface layer roughly 0.5 millimeter thick across the entire front of the spacecraft. For a gram-scale probe the size of a postage stamp, 0.5 millimeter of erosion across the front surface is significant. For a ship large enough to carry human beings, the geometry scales up dramatically, and the shielding requirements grow with it. The Starshot team's proposed solution: mount a thin shield of graphite, or beryllium copper a few millimeters thick, on the front of each probe to absorb the impacts. And because the team calculated that some probes would inevitably be destroyed outright by the rare encounter with a slightly larger dust grain, the plan calls not for one probe but for a fleet of approximately 1,000, designed with redundancy built in, knowing some would not survive. Redundancy is a viable strategy when you are launching thousands of chips. For a ship carrying human beings, redundancy of that kind does not exist. Now comes the element of this journey that even the most technically prepared mind finds difficult to fully absorb. Not because it is complex, but because it is so far outside anything human experience has ever prepared us for. At the speeds required for any meaningful interstellar mission, the physics of time itself changes. Time dilation, first predicted by Albert Einstein in 1905 and confirmed by every experiment ever designed to test it, is this: time does not pass at the same rate for all observers. The faster you move, the slower your clock runs compared to someone who is stationary. Not because the clock is defective, not because of any illusion or trick of perception, because of the fundamental structure of space-time. The effect is real, physically present in the universe, and measurable at any speed. It is simply too small to notice until speeds approach a meaningful fraction of the speed of light. GPS satellites orbiting Earth at roughly 14,000 kilometers per hour, about 14 kilometers per second, must have their onboard clocks corrected by 7 microseconds every single day to account for the time dilation produced by their orbital speed. Without that correction, GPS navigation would accumulate positioning errors of several kilometers every day. The engineers who built GPS had to take Einstein's equations into account to make the system work. Time dilation is not theoretical. It is the reason your phone can find you on a street corner. Now scale that speed upward toward 10% of light speed, or 20, or 90. At 10% of light speed, a traveller's clock runs about 0.5% slower than a clock on Earth. On a 40-year journey, The traveller arrives roughly 2.5 months younger than they would have been if they'd stayed home. Real, but negligible. At 20% of light speed, starshot speeds, the difference reaches about 2%. Over a 21-year journey, the probe or its travellers would experience roughly 20.6 years, while Earth experiences 21. Close enough that the difference barely matters, but for a crewed mission that somehow achieved 90% of light speed, the territory where fusion or antimatter drives theoretically operate, the effect becomes impossible to ignore. At 90% of light speed, the Lorentz factor, the multiplier that describes how profoundly time slows, reaches approximately 2.3. For every year that passes aboard the ship, about 2.3 years pass on Earth. A journey to Proxima Centauri at 90% of light speed would take just over 4.5 years in Earth's reckoning, but the crew would experience only about 2 years. They would arrive, if everything worked, 2 years older than when they left. The Earth would be more than 4 years further along. At 99% of light speed, the Lorentz factor reaches approximately 7. 1 year for the travellers equals 7 years on Earth. A round trip to Proxima Centauri and back, in the traveller's experience, might take less than 2 years. The people who launched them would be 14 years older when they returned. Children who were 10 years old at departure would be in their mid-20s. The world the crew left would be not quite the same world they came home to. This is the twin paradox. Documented, verified, not a paradox at all, but a genuine asymmetry in how time passes for observers in different states of motion. It has been confirmed by precise atomic clock experiments on aircraft. The asymmetry is real, and for any crewed mission that achieves genuinely relativistic speeds, it transforms the emotional and social meaning of the journey in ways no engineering specification can fully prepare anyone for. You leave a world, you return to a world that has moved further through time than you have. The gap between those two facts is not metaphor, it is physics. Now, add the silence of distance. Any signal sent from a ship at Alpha Centauri to Earth travels at the speed of light and takes 4 years and 2 months to arrive. A reply takes another 4 years. A single round-trip exchange of information takes over 8 years. Not due to any technical limitation, due to the distance and to the fact that light speed is the fastest anything can travel. For the Starshot probe, this creates a very specific operational reality. The probe passes through the Alpha Centauri system in approximately 40 hours, the entire window during which its instruments can observe, measure, photograph and collect data before the system is behind it, and it has flown on into deeper space. No course corrections are possible from Earth during that window. By the time a signal from Earth could arrive, the probe has already completed its flyby and moved on. The data it sends home will take 4 additional years to arrive. Mission operators on Earth will have to wait more than 25 years from launch before receiving the first images. For a crewed ship, the communication delay creates a more profound isolation than any psychological study of confined groups has ever fully grappled with. No live conversation with family on Earth, no real-time guidance from home for any crisis, no hope of rescue arriving in less than decades. The people aboard are entirely, completely on their own, in knowledge, judgment and survival, from the moment of departure until the moment any return signal might reach someone who could help. Which of course, it never could, in any time frame that matters. And then there is the final physics trap, the one that closes on any mission at the end. Speed is the goal. Speed is the solution to the time problem. Speed is everything. But you cannot simply arrive at high speed. You have to stop. Decelerating from 20% of light speed, or 50%, or 90% requires the same expenditure of energy as accelerating to that speed in the first place. The fuel costs double. Every challenge of acceleration becomes equally a challenge of deceleration. The ship that was half empty at the midpoint of the journey has to somehow carry enough propellant to do the entire second half, while already travelling at a speed that makes every environmental hazard more severe. The Breakthrough Starshot probe sidesteps this completely. It is a flyby mission. It does not stop. It photographs, it collects, it transmits, and it flies on into the dark for 40 hours. For a crewed mission, a flyby is not an option. The crew must decelerate, orbit, land, or at minimum slow to a speed at which they can study the system in detail rather than glimpsing it as it blurs past. And then there are failures. Equipment failures, structural failures, medical emergencies, the entire spectrum of things that can go wrong with any complex system over decades of operation in a hostile environment. Every one of them must be solvable by the people and resources aboard. No part can be ordered and delivered. No specialist can be consulted in real time. No rescue mission arrives in less than 8 years of light travel time minimum, and in practice, decades more. The ship is its own civilization, and that civilization must be entirely self-sufficient in every conceivable emergency for the entire duration of the journey. So here is what physics places between us and the nearest star: galactic cosmic rays streaming continuously from every direction, impossible to fully shield against, accumulating biological damage across every living cell for the entire duration of any crewed mission. A sparse medium of gas and dust that, at the required speeds, delivers a relentless erosive bombardment on every forward-facing surface. A relativistic regime in which time flows differently for travelers on Earth, creating an asymmetry that grows deeper the faster the ship moves until the crew returns to a world that has aged more than they have. A communication delay that imposes complete isolation from the moment of departure. And at the end, the requirement to decelerate at the same cost as the entire acceleration in a system where no external help exists. None of these threats are unsolvable in principle. Engineers and physicists have proposed approaches to each of them: shielding strategies, material designs, navigational protocols. But each solution carries its own mass and cost, and solving all of them simultaneously for a crewed mission, one that must sustain human life across decades or generations, remains far beyond anything currently within reach. The void is not empty. The void has physics, and yet there is something important about the way these constraints are stated. Every single one of them exists inside the framework of physics as we currently understand it. They are real, but they are also bounded by what we know. What physicists have also been doing, quietly and rigorously, is asking whether the deeper structure of space-time itself might contain features that change the calculation. Not ways to break physics, ways to work within physics at a level we have not yet reached. Black holes as gravitational machines of extraordinary energy. Wormholes, theoretical tunnels through the fabric of space-time connecting two distant points. Geometries of space that contract in front of a ship and expand behind it, effectively moving the ship without the ship having to push against the void at all. These ideas live at the frontier of what general relativity permits, and whether any of them are real, accessible, or buildable by any civilization is one of the most open and genuinely extraordinary questions in all of science. What the physics actually allows, and what the universe might genuinely permit, is where we go next. What physics actually allows is not what common sense suggests. Every constraint we have examined so far, the tyranny of the rocket equation, the speed limit of light, the radiation, the dust, the deceleration problem, each of these exists because of the rules of physics as we currently understand them. And those rules are real. They are verified. They are not going away. But here is what is remarkable. The same body of physics that creates every one of those barriers also contains, buried in its mathematics, descriptions of structures and geometries that seem to work around them, not by breaking the rules, by operating at a level of the rules that humanity has never reached. And some of the most rigorous theoretical physicists in the world, people publishing in peer-reviewed journals, presenting at serious academic conferences, working at places like Caltech and Columbia and MIT, have been quietly, carefully examining whether any of those deeper structures might be real, and if real, whether they might ever be usable. The honest answer, as of now, is some might be real, and none are currently usable. But the gap between those two things is not forever. Before exploring these concepts, one important distinction must be held clearly in mind. Einstein's equations of general relativity describe the relationship between matter, energy, and the geometry of space-time. They are extraordinarily powerful. They predicted black holes decades before any were observed. They predicted gravitational waves, which went undetected until the LIGO Observatory finally heard the collision of two black holes in 2015, exactly as the equations described. When physicists say that a given concept is a solution to Einstein's equations, they mean something precise. The mathematics of general relativity can produce a space-time geometry that has these properties. This is not the same as saying the thing exists. Einstein's equations also technically allow for rotating universes, negative energy densities, and structures that connect distant regions of space. The mathematics is consistent. Whether nature chooses to instantiate those solutions, whether the physical universe actually builds them, is a separate question, one that mathematics alone cannot answer. With that in mind, the concepts that follow deserve to be taken seriously. They are not science fiction dressed up in equations. They are genuine mathematical structures within established physics, whose connection to physical reality remains deeply, genuinely open. Begin with the concept closest to our current engineering capability, because it is also the most honest about its limitations. Gravitational slingshot maneuvers are not theoretical. They work. Every major interplanetary mission since the 1970s has used them. Voyager 1 and Voyager 2 swung past Jupiter, harvesting energy from the planet's enormous orbital momentum around the Sun, and used that freely borrowed energy to gain the speed needed to cross the outer solar system. New Horizons used Jupiter the same way to reach Pluto. The Parker Solar Probe used Venus 7 times. Gravity assists are proven, operational spacecraft propulsion, consuming no propellant from the ship itself, borrowing instead from the motion of massive bodies. The question is, can this principle be scaled up to reach interstellar speeds? Here, the answer becomes sobering. Around a planet like Jupiter, our best solar system slingshot, the maximum speed gain equals approximately twice Jupiter's orbital velocity around the Sun. Jupiter travels at about 13 kilometers per second, about 8 miles per second, in its orbit. The maximum speed addition from a Jupiter slingshot is therefore roughly 26 kilometers per second, useful for planetary missions. For interstellar travel, barely a rounding error. What about using the Sun itself? In 1988, physicist Gregory Matloff calculated what would happen if a spacecraft plunged to within about 1.5 million kilometers of the Sun's surface, roughly the same distance at which the Parker Solar Probe operates, and fired its engines at the exact moment of closest approach, when its velocity was at its absolute maximum. This combination of maneuvers, called the Oberth effect, produces a dramatically larger speed increase than either approach alone. Matloff's result? An exit velocity of roughly 110 kilometers per second, about 68 miles per second. That is genuinely fast. Parker Solar Probe at its peak reached around 190 kilometers per second, in the same ballpark. But even at 110 kilometers per second, the journey to Alpha Centauri would take approximately 11,000 years. Faster than Voyager, still measured in civilizational timescales. The question is then, are there even more extreme gravitational machines available? In 1963, theoretical physicist Freeman Dyson explored this in a paper titled Gravitational Machines. He described what would happen if a spacecraft made a close pass around a binary star system, 2 stars orbiting each other, instead of a single stationary star. The energy available for slingshot gain depends on how fast the bodies are moving. White dwarf stars in tight binary orbits move much faster than planets. Neutron stars, the ultra-compact remnants of massive stellar explosions, each with roughly the mass of the Sun compressed into a sphere about 20 kilometers across, or about 12 miles, in close binary orbits can whip around each other with extraordinary speed. Dyson calculated that a spacecraft making a close pass through a binary neutron star system could, theoretically, be ejected from it at approximately 27% of the speed of light, 81,000 kilometers per second, or about 50,000 miles per second. At that speed, Alpha Centauri would be roughly 16 years away. More recently, astrophysicist David Kipping of Columbia University proposed a variation he called the halo drive, using a black hole binary, where photons directed at the edge of the event horizon are reflected back by frame dragging, the way rotating black holes drag space-time itself around them, potentially providing a kind of gravitational mirror that could accelerate a spacecraft without any onboard fuel at all. But here is the engineering reality. Binary neutron stars do not exist anywhere near Earth. The nearest known candidates are thousands of light years away, which means reaching the slingshot itself would require the very interstellar capability we're hoping to build, and navigating close to two neutron stars orbiting each other at fractions of the speed of light, generating gravitational wave emissions powerful enough to be detected across the galaxy while managing the tidal forces and radiation environment of an extreme relativistic environment. This describes a level of engineering so far beyond anything we possess that calling it speculative would be generous. The slingshot principle is real. The slingshot, at interstellar scale, requires objects and distances we cannot yet reach. Now consider something stranger. In 1994, a theoretical physicist named Miguel Alcubierre, working on his doctoral research in numerical relativity at the University of Wales in Cardiff, published a paper in the journal Classical and Quantum Gravity that proposed a solution to Einstein's field equations describing an entirely new kind of motion. Alcubierre's key insight was this: the speed of light is an absolute limit on how fast anything can move through space, but space itself is not bound by that limit. The universe has been expanding since the Big Bang, and distant regions of the cosmos are receding from us faster than light, not because anything is moving through space faster than light, but because space itself is expanding between us and them. What Alcubierre asked was, could space be made to do something similar on a local, controlled scale? His metric, his mathematical description of the space-time geometry, describes a bubble of flat, normal space wrapped in a shell of curved space-time. Ahead of the bubble, space is compressed. Behind it, space is expanded. The bubble, carried by this wave of curvature, effectively surfs through space rather than moving through it. Anything inside the bubble never moves locally faster than light, yet from the outside it arrives at its destination at whatever speed the bubble is moving, which Alcubierre's equations place at no theoretical limit at all. The crew inside would experience no acceleration, no crushing g-forces, no time dilation from their perspective. The bubble is their local environment, and it simply moves. When Alcubierre's paper was published, it produced a genuine stir in the theoretical physics community. Here was a metric that existed within the framework of general relativity, that allowed effective, faster-than-light travel without violating the local speed of light, with no exotic new physics required, just a particular configuration of space-time. But here is where it gets painful. Producing that configuration of space-time requires matter with negative energy density, exotic matter, material that, in the relevant quantity, does not appear to exist in our universe in any known form. Alcubierre's original calculation found that a warp bubble large enough to contain a 200-meter ship would require an amount of exotic matter exceeding the mass energy of the entire observable universe. That is not engineering impractical. That is physically impossible by any measure. Subsequent work by theoretical physicists has refined the equations and dramatically reduced the exotic matter requirement by many orders of magnitude. But the requirement remains. An exotic matter with negative energy density on macroscopic scales has never been produced, detected, or confirmed to exist. The Casimir effect, a measurable quantum phenomenon in which two very closely spaced metal plates in a vacuum experience a tiny attractive force, has been interpreted by some physicists as evidence that negative energy densities can exist at quantum scales. The effect is real and measured, but it produces negative energy over distances of nanometers, billionths of a meter, in quantities so infinitesimally small that scaling them to interstellar propulsion requires physics we do not understand. More recently, in 2021, researchers Alexei Bobrik and Gianni Martire published a peer-reviewed paper in Classical and Quantum Gravity proposing what they called a physical warp drive, the first general model of a warp bubble that uses only positive energy, no exotic matter at all. In 2023, a team at the University of Alabama in Huntsville, led by Dr. Jared Fuchs in collaboration with the Applied Physics Group in New York, published an additional peer-reviewed framework for a subluminal constant velocity warp drive, again requiring only normal positive energy matter within the bounds of known physics. The catch: these drives cannot exceed the speed of light. They are subluminal, meaning they travel below light speed. The exotic geometry of space-time movement is retained. The faster-than-light shortcut is not. What they offer instead is a form of propulsion in which passengers experience no acceleration forces. The warp bubble shields them from the physics of rapid velocity change. Practically significant, potentially, but not a solution to the time problem of interstellar travel. The warp drive has moved from pure science fiction to genuine, peer-reviewed theoretical physics. Whether it ever moves further depends on physics we do not yet know. In 1935, Albert Einstein and his colleague Nathan Rosen were working through the implications of general relativity when they discovered that the mathematics describing a black hole, the equations of a massive, gravitationally extreme object in space, contained something unexpected. The solution had not one region of curved spacetime but two regions of space connected by a bridge, a mathematical tunnel running through the geometry of the universe from one point to another. They called it an Einstein-Rosen bridge. Decades later, physicist John Archibald Wheeler, who gave the atom bomb its name and coined the phrase black hole, gave this structure a more evocative name. He described it as a wormhole, a tunnel bored through the fabric of space-time, the way a worm bores through an apple, taking a shortcut between two distant points on the surface without travelling along the surface at all. Picture space-time as a flat sheet of paper. 2 points on that sheet might be separated by enormous distance. But if the sheet could be folded, if space-time itself could be bent, those 2 points might be brought adjacent with only a short tunnel connecting them. A wormhole is the tunnel. It does not bypass the distance by travelling faster. It changes the effective distance by going through the geometry. In 1987, physicist Kip Thorne, who would go on to win the Nobel Prize in Physics for his work on gravitational waves, worked out the mathematics of a traversable wormhole. The inspiration came directly from Carl Sagan, who was writing his novel Contact and wanted to know whether a wormhole might be physically defensible as a plot device. Thorne's calculations showed that a traversable wormhole, one that stays open long enough for something to pass through, is mathematically consistent with general relativity. The solution exists, the math works, but keeping it open requires the same ingredient as the Alcubierre drive: exotic matter with negative energy density. Without that exotic matter, the wormhole's throat, the narrow connecting region between the two openings, collapses faster than the speed of light. Anything attempting to enter from either side would find the passage sealed before it could cross. The original Einstein-Rosen bridge is not traversable for precisely this reason. It collapses instantly, and nothing, not light, not information, not any physical object, can transit it. With sufficient exotic matter, The wormhole's throat could theoretically be held open. A traveller entering one mouth would emerge from the other, having crossed 4 light years in the time it took to walk down a short corridor. The 4 years of transit time would not simply be reduced. It would be replaced by whatever time the passage through the throat required. No wormhole has ever been detected. No exotic matter of the required kind has ever been produced. Whether wormholes of any kind exist in nature, naturally, formed perhaps in the turbulent geometry of the early universe, is unknown. Whether they could be artificially created or stabilized is deeply unknown. The mathematics permits them. The universe may or may not. Against all of these exotic possibilities, one strategic alternative stands out precisely for its pragmatism. Rather than attempting to solve the interstellar problem with a single grand engineering achievement, one ship, one mission, one attempt, the swarm approach proposes distributing the mission across thousands of small probes, accepting that some will fail and relying on redundancy to ensure that the knowledge returns home. Breakthrough. Starshot's plan called not for one laser sail, but for a fleet of approximately 1,000 identical gram-scale probes, specifically because the team calculated that dust collisions and other hazards would destroy some fraction of them during the journey. The mission's success would not depend on every probe surviving. It would depend on enough of them surviving. The swarm architecture changes the risk calculus of interstellar travel in a fundamental way. A single ship that fails means total loss. A fleet of 1,000 probes that loses 400 still delivers data from 600. The scientific return survives the physical losses. Taken further, a swarm strategy also makes scientific sense at the destination. Multiple probes arriving at slightly different times from slightly different angles would collectively build a far richer picture of the Alpha Centauri system than any single observer could. And from a communication standpoint, a synchronized swarm of probes could potentially combine their faint transmissions in phase, arriving at Earth simultaneously and constructively, producing a signal far stronger than any individual chip's laser communicator could manage alone. The swarm approach does not solve the problem of getting there, but it changes what getting there means. Not one emissary, but many. Not success or failure, but a gradient. The universe may be hostile to individual missions while being hospitable to distributed ones. So here, honestly, is where physics leaves us with the exotic alternatives. Gravitational slingshots work. At planetary scale, they are proven. But the gravitational machines needed for interstellar speeds do not exist near Earth. The solar Oberth maneuver reduces the journey from 74,000 years to 11,000. Real progress, still measured in ages. The Alcubierre warp drive is a genuine solution to Einstein's equations. Researchers are actively working on versions that require no exotic matter. None of those versions can exceed the speed of light. The faster-than-light version requires exotic matter that has not been found in the universe in any useful quantity. Wormholes are mathematically real. Physicist Kip Thorne showed that they are consistent with general relativity if exotic matter can keep them open. No. Wormhole has been detected. No exotic matter capable of keeping one open has been produced or confirmed to exist. Swarm probes represent the most strategically mature alternative, distributing risk, distributing benefit, accepting that the journey is one way and the results come in fragments rather than a single grand arrival. The gap between what physics permits on paper and what any civilization known to us has ever built is extraordinary. But that gap is not the same as impossibility. It is the gap between where we are and where we might one day reach. And understanding it clearly is the beginning of knowing what would need to be true for any of these paths to open, which leaves us with the question that has been present since the first chapter of this journey, and which none of the physics or engineering has yet answered. We know a destination exists. We know it has planets. We know at least one of those planets sits at the right distance from its star for liquid water. We have spent this entire journey understanding the scale of what separates us from it, the distance, the propulsion limits, the human requirements, the physical hazards, the exotic alternatives, and found that every road either leads to an answer measured in thousands of years or depends on physics we do not yet possess. But what is actually there? What would we find if we arrived? The Proxima Centauri system, the nearest fire in the sky, is not a blank slate. Scientists have been studying it intensely for a decade with the best instruments available to us, and what they have found is a picture of a world that is genuinely possible, genuinely uncertain, and genuinely unlike anything in our own solar system. A world that might harbour oceans, or might be a scorched and airless rock. A world that might have answered the deepest question in science, or might confirm that we are profoundly alone. The nature of what awaits is not merely a matter of curiosity, it is the entire reason the journey matters. The nature of what awaits at the nearest fire in the sky is not merely a matter of curiosity. Every propulsion concept we have examined, every human cost we have weighed, every physical hazard we have reckoned with, all of it leads here, to the actual question, the one that the journey exists to answer. What is Proxima Centauri b? Not what do the models suggest, not what might be possible under favourable assumptions, but what is actually there, on the surface, in whatever atmosphere survives, in whatever pools or oceans or bare exposed rock the planet has produced in the 4 billion years it has been circling its violent ancient star. Scientists cannot yet answer this directly. No instrument on Earth or in orbit can resolve the surface of a world 4 light-years away. What they can do, and have been doing intensely since the planet's discovery in 2016, is build models, run simulations, examine every piece of indirect data available, and from that work a picture has emerged. Not a certain picture, a divided one, where the same basic facts lead different researchers to profoundly different conclusions. A picture that is honestly, stubbornly uncertain, and that uncertainty is not a failure of science. It is a precise description of how much we do not know, and how much depends on what we find. Begin with the confirmed facts and hold them clearly. Proxima Centauri b is a rocky planet with a minimum mass of at least 1.06 times that of Earth. It orbits its star at a distance of approximately 7.5 million kilometers, or 4.6 million miles. That orbit takes just 11.2 Earth days to complete. At that distance, gravity almost certainly imposes something called tidal locking on the planet, meaning the same face always points toward Proxima Centauri, the way the same face of the Moon always points toward Earth. One side of the planet lives in permanent starlight, the other in permanent night. Not a cycle of day and night, a permanent divide. Proxima b sits within its star's habitable zone, the range of orbital distances where temperatures might allow liquid water to exist on a surface. The planet receives about 65% of the radiation that Earth receives from our Sun. Based purely on that radiation balance, the equilibrium surface temperature, the temperature the planet would settle at without any atmosphere, works out to roughly minus 39 degrees Celsius or minus 38 degrees Fahrenheit. Cold, but potentially modifiable by an atmosphere the way Earth's own atmosphere raises surface temperatures well above what raw solar input alone would produce. What we do not know, whether Proxima b has an atmosphere at all, whether it has water, whether it has a magnetic field, whether its interior is geologically active, whether any of the conditions required for life ever existed or were never there. Every significant question about the planet remains, as of now, genuinely unanswered. Start with the most hopeful picture first, because it is not fantasized. It is the product of serious 3-dimensional climate modeling by teams at NASA and major research universities, published in peer-reviewed journals. Anthony Del Yanio of NASA's Goddard Institute for Space Studies and colleagues ran 18 separate climate simulations of Proxima b in 2019, using some of the same computational tools developed for studying Earth's climate. Their models varied ocean depth, atmospheric composition, greenhouse gas concentrations, and ocean salinity. The results surprised many who expected a tidally locked world to be mostly hostile. In almost every simulation, liquid water persisted across some significant fraction of the planet's surface. The scenario that repeatedly emerged is what scientists have called an eyeball Earth. The side of the planet perpetually facing Proxima would receive constant, unchanging starlight, a strange ruby-red light given the star's deep orange-red colour, far dimmer than our Sun but casting its warmth continuously across a single hemisphere. Under that permanent light, surface temperatures in the substellar region, the point directly facing the star, could reach conditions suitable for liquid water. Meanwhile, the dynamic circulation of both atmosphere and ocean would carry heat from the lit side toward the dark side, warming parts of the terminator, the ring where light and darkness meet, where temperature transitions from scorching to frozen. Picture this. Standing near the terminator of Proxima b, the star would be perpetually near the horizon, never rising, never setting. The sky behind you, toward the night side, would be absolute black. The sky ahead, toward the lit hemisphere, would glow a deep, permanent amber red. At your feet, if the models that include a circulating ocean are correct, water might lap at a coastline that never changes with the season, because there are no seasons. The tides, driven by Proxima's immense gravitational pull at that close distance, would be extraordinary, washing over coastal regions with a power that dwarfs anything on Earth. Whether life could exploit that churning, chemically active interface between land and ocean is a question not yet answerable from this distance. Del Yenio and his team found that an ocean-covered Proxima b with sufficient salinity could maintain a much broader liquid surface than previous static ocean models had suggested, even at nightside equatorial latitudes, where ocean currents carrying warm water from the dayside could prevent freezing. The oceans, they concluded, could be dominated by salt-adapted life if the right conditions were met. But here is the problem. The right conditions depend on one thing above all others, an atmosphere, and the atmosphere of Proxima b is where the picture becomes deeply, seriously contested. The star that Proxima b orbits is not gentle with the world it holds closest. In 2017, Catherine Garcia Sage at NASA's Goddard Space Flight Center led a team that modeled what would happen if they took Earth, with Earth's actual atmosphere, magnetic field, and gravity, and placed it in Proxima b's orbit. They published their results in the astrophysical journal Letters. The conclusion was sobering. At that orbital distance, Proxima Centauri's radiation environment strips atmospheric gas at a rate up to 10,000 times faster than the Sun strips Earth's uppermost atmosphere. Not slightly faster, 10,000 times faster. Even during average activity, not the superflares but ordinary daily radiation, the atmospheric loss rate for any Earth-like atmosphere at that location would be catastrophic on geological timescales. The research suggested that an unprotected atmosphere might be completely stripped within 10 million years. And 10 million years is a brief moment compared to the age of Proxima Centauri b. The planet is billions of years old. Proxima itself, as a red dwarf, will outlive our Sun by an almost incomprehensible margin. The question of how an atmosphere could have survived 4 billion years of this radiation environment, or whether it could have been regenerated by volcanism and outgassing after being stripped, is deeply uncertain. The pre-main sequence problem makes it worse. Early in its history, before Proxima Centauri settled into its current stable state, the star was significantly more luminous, hot enough that a planet at Proxima b's current orbit would have been inside a runaway greenhouse zone. Scientists estimate Proxima b may have spent roughly 169 million years, far longer than Earth's entire evolutionary history before complex life, subjected to radiation intense enough to vaporize any oceans that tried to form. Between 3 and 10 Earth oceans worth of water could have been lost in that early period, alone. And yet, scientists studying the other side of this debate point out that Venus, orbiting much closer to the Sun than Earth with no magnetic field, maintains a thick, dense atmosphere through volcanic outgassing. A geologically active Proxima b could potentially replenish its atmosphere from the inside, continuously replacing what the star strips away from the outside. The planet's large mass makes geological activity likely. Whether the replenishment could keep pace with the stripping over billions of years through superflares erupting without warning every few hours is one of the most genuinely contested questions in exoplanet science. In 2025, new research suggested Proxima b might possess a magnetic field generated by a liquid iron core similar to Earth's. If confirmed, and it has not yet been, that magnetic field could deflect much of the stellar wind and slow the atmospheric loss dramatically. The evidence is not conclusive. Detecting a magnetic field on a planet 4 light-years away pushes the absolute limits of current technology. But the possibility is real enough to keep the habitability question open. 2 groups of serious scientists, using serious models, have reached different conclusions about whether Proxima b could support life. Both sides have published in peer-reviewed journals. Both sides have compelling arguments. The debate is not resolved, and from Earth, with our current instruments, it may not be resolvable. Suppose we arrived. Suppose the journey, however it was accomplished, by whatever civilization eventually found the propulsion, built the ships, crossed the void, found on the surface of Proxima b, or in its oceans, or buried beneath its rock, something unmistakable, something that converted carbon and oxygen in patterns too precise to be chemistry alone, something that reproduced, something alive. The scientific consequences would be the most profound in human history. Here is why. Life, on Earth as far as we know, arose once. A single origin, a single chemistry, the familiar DNA-based molecular machinery that connects every living thing on this planet, from bacteria in volcanic vents to sequoia trees to the creature reading these words. We have no second example of life emerging independently. That single data point makes it almost impossible to know whether life is a common, inevitable outcome of chemistry wherever conditions are right, or an extraordinary accident that happened on this one world and may never have happened again. Finding life at Proxima b would change that immediately. If life arose independently on a planet orbiting the nearest star to our Sun, a star that is, in the context of our galaxy, essentially our immediate neighbour, then the implication is powerful. Life does not require Earth-specific conditions. Life does not require a yellow sun, or a particular mass planet, or any of the specific circumstances of our solar system. Life emerges wherever something close to the right conditions persist for long enough. And if that is true at the nearest star, it is almost certainly true across the galaxy. Among the 200 to 400 billion stars of the Milky Way, each surrounded by its own worlds, something like life would be not a rarity but a statistical certainty. The galaxy would be alive. This would be what scientists sometimes call the second genesis, a second independent origin of life. The discovery of a second genesis, anywhere in the cosmos, would constitute proof that life is a natural outcome of chemistry rather than an extraordinary accident. Frank Drake's famous equation, proposed in 1961 to estimate the number of communicating civilizations in the galaxy, contains a term for the fraction of habitable planets where life actually arises. That term has no empirical value. No data supports it. Finding life at Proxima b would provide the first data point, and it would be a generous one. What kind of life? Possibly microbial, possibly nothing more than single-celled organisms adapted to the radiation, the tidally locked climate, the extreme tidal forces. Possibly more complex, if the planet's history allowed it. The detection of any life, any biology operating on any scale, would be the answer to the oldest question our species has ever asked. But suppose we arrived and found nothing. Suppose the surface of Proxima b turned out to be exactly what the pessimistic models suggest: a bare, airless rock, or a world with a thin, toxic atmosphere and no liquid water anywhere on its surface, no life, no chemistry approaching biology, no signals of any kind, either past or present. Just the permanent half-light, the relentless radiation, the rock, and silence. This outcome would not be a defeat, not scientifically. An empty Proxima b would answer questions too. But the questions it would answer are some of the most unsettling in astronomy. In 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question so simple it stopped conversation. Where is everybody? If the galaxy is old, and if stars with planets are common, and if life is a natural outcome of chemistry, then civilizations with technology should have had billions of years to expand, to signal, to leave their mark. Yet we have detected nothing. No signal, no artifact, no sign. The silence is total. This is the Fermi paradox, the mismatch between what logic suggests should be a populated galaxy and what observation finds. Nothing. One of the most disturbing proposed explanations is called the Great Filter, proposed by economist and thinker Robin Hanson in 1996. The Great Filter is whatever step in the chain from chemistry to civilizations is so extraordinarily improbable that almost nothing gets through it. Either the difficult step lies behind us, meaning abiogenesis, the origin of life itself, is astronomically rare, and we exist as an extraordinary exception, or the difficult step lies ahead of us, meaning it is the step from technological civilization to interstellar presence that almost nothing survives. If Proxima b, the nearest habitable zone planet, in the most favorable position in the galaxy for finding life, is empty, the most natural interpretation is that the Great Filter lies somewhere early, that life arising from chemistry is extraordinarily hard, that we may be one of the very few inhabited worlds in a galaxy of billions of planets, that our loneliness is not an illusion, that finding would be simultaneously humbling and strange. Humbling because it would mean life is not inevitable, not the natural outcome of chemistry running its course, but something more rare and more precious than any model currently suggests. Strange because it would mean that we, this one world, orbiting this one ordinary star, producing these specific creatures with their science and their questions and their telescopes, are not typical. We are the exception, perhaps an extreme exception, and understanding that, truly absorbing it, would change not just science but the way any civilization thinks about its own existence and its obligations to itself. So this is what awaits at Proxima b, as science currently understands it. A rocky world, probably tidally locked, probably subjected to intense radiation for its entire history, possibly with liquid water on its surface under certain atmospheric conditions, possibly with a magnetic field that could have shielded it from some of that radiation, possibly with volcanism that could have replenished its atmosphere through the flares and the stripping, or possibly none of these things, a bare, exposed surface with no protection and no water, scorched clean by 4 billion years of a violent star. Whether life is there, or was there, or never had a chance, we do not know. We cannot know from here. The James Webb Space Telescope and the next generation of extremely large telescopes currently under construction may one day be able to detect the chemical signatures of an atmosphere around Proxima b, if one exists, and search for what scientists call biosignatures, combinations of gases like oxygen and methane that suggest living chemistry at work. These instruments push the absolute limit of what is currently possible. They may provide hints in the coming decades, but a definitive answer about the presence of life on Proxima b may require something we do not yet have, the ability to go there, and that is the circle that closes at the end of this journey. The destination that gave the journey its meaning is the same destination that makes the journey necessary to understand. This is the full weight of it. 4 light-years away, a world sits in the permanent half-light of a violent red star, holding in its rock and atmosphere and possible oceans the answer to the deepest question our species has ever asked, and we cannot reach it. Not yet. Perhaps not in any of our lifetimes. Perhaps not for centuries. But the question itself, the fact that we are able to ask it, that we have found the world, identified its orbit, measured its mass, modelled its climate, debated its atmosphere, and stood here on Earth looking outward and knowing precisely where to look, is itself a kind of extraordinary thing. A species that emerged on one world, looked up at the sky, and learned to read what it saw well enough to find another world at the nearest star. That is what we have done. What it means, not just scientifically, but for everything we are and everything we might become, and what our existence here says about the nature of the universe that produced us. That is the final question, and it cannot be answered by an equation, or a model, or a telescope. It can only be answered by sitting quietly with everything we have learned and letting it settle. Sitting quietly with everything we have learned is not a passive act. By the time any traveller reaches the end of a long journey, physically or intellectually, they carry something they did not have when they began. Not just information, weight. The weight of understanding something fully rather than glancing at it from a distance. The weight of knowing not just that a thing is difficult, but why. The weight of having followed an honest reckoning all the way to its conclusion without flinching. We have done that here. We followed the tension in the word nearest all the way to its core. We found a system of 3 stars, one of which has planets. We measured the scale of the void between us and them with every comparison we could bring to bear, and the distance remained what it is. We inventoried every propulsion concept humanity has seriously proposed and watched each one arrive at a different shape of the same fundamental problem. We entered the hull in imagination and asked what it would take to keep human beings alive, sane, and purposeful inside a sealed world for the length of a civilization. We walked through the physical environment of interstellar space and felt what it would cost to survive it. We peered at the deeper structure of physics and found mathematics that permits the extraordinary, but cannot yet be made to yield it. And at the end, we stood before a world 4 light-years away and held the question of whether it might be alive. What remains is not a summary. What remains is the meaning of all of it, the one thing that cannot be reduced to a number or modelled in a simulation. The journey to Alpha Centauri is terrifying. That word was placed in the title of this story deliberately, because it is accurate, and because it means more than most people assume when they first hear it. The terror is not the darkness between the stars, not the radiation or the dust or the isolation. Those are formidable obstacles, but they are engineering problems. The terror is existential. The journey reveals something about the relationship between our species and the universe that is difficult to hold in the mind all at once. We are large enough to understand the distance. We have built instruments sensitive enough to detect a planet 4 light-years away by the faint wobble it causes in a star's velocity, a wobble of 5 kilometers per hour measured across interstellar space. We have sent probes that are now, genuinely, outside the solar system. We have modelled the atmosphere of a world we have never visited and published those models in peer-reviewed journals. We have proposed, funded, and partially built technologies intended to reach that world within a human lifetime. We are remarkable in the genuine sense of that word, and we are also small enough that the distance humbles us absolutely. Every measure of scale we have applied, from evolutionary timescales to the mass of the observable universe, has returned the same message, stated in different languages. You are here. Alpha Centauri is there. The space between those 2 facts is not empty. It is full of physics, and that physics has not finished telling us what it will cost. These two things are both true at once. We are remarkable enough to understand the challenge. We are not yet capable of meeting it. That is not a failure. That is the honest situation. And it is one of the most interesting situations our species has ever occupied. Every generation of human beings that has ever looked at the night sky has looked toward Alpha Centauri, even when they did not know it was there. The Scottish astronomer Robert Innes discovered Proxima Centauri, identified it as a distinct star from its companions, and confirmed it was the closest to our Sun in 1915. For all of the thousands of years of human civilization before that, people looked at what appeared to be a single brilliant star in the southern constellation of Centaurus, and did not know they were looking at a triple system, did not know the nearest one was invisible to the naked eye, did not know there were planets, and yet something drew them outward anyway, long before exoplanets were confirmed, long before spectroscopy could analyze the composition of a stellar atmosphere, long before we had any instrument that could see anything beyond our own solar system. Something in the human mind consistently, persistently, and apparently inescapably turned toward the sky and asked, what is out there, and could we reach it? This is worth sitting with. The drive to look outward is not a recent cultural development. It predates science. It predates writing. Archaeological evidence of astronomical knowledge appears in human cultures going back tens of thousands of years, in the alignment of burial mounds, in the placement of standing stones, in the careful recording of celestial cycles. The sky was the first shared reference that all of humanity had in common. And among the questions that sky provoked, the question of distance, of what it would mean to cross it, appears again and again in every tradition we have record of. The modern version of that drive is not different in kind. It is only more precise in its tools and more honest about its obstacles. We no longer look at Alpha Centauri and imagine crossing to it easily. We know what crossing it would require, and we look anyway, because looking and knowing and reaching even as far as understanding can go is what we are. It is what has always defined us. Consider what interstellar travel, if it ever happened, would actually represent. A ship leaving for Alpha Centauri, by any propulsion method in the range of what physics currently permits, departs from a species that has never travelled beyond its own solar system. It carries with it, in its hull, in its crew, in its libraries and its culture, the accumulated knowledge of a civilization that has existed for perhaps 10,000 years in its current form. A civilization that was, not very long ago by cosmic standards, entirely confined to a single rocky planet orbiting an unremarkable star in an outer spiral arm of an average galaxy. That ship crosses an unimaginable emptiness, not metaphorically, physically. A void in which the nearest object of any kind is the destination itself. No landmark, no waypoint, no harbour to shelter in if things go wrong. Just the ship and the people inside it, and the physics of the void pressing against the hull from every direction. And then, if the engines hold, if the shields hold, if the generations inside remain coherent enough to maintain purpose across decades or centuries, something arrives at Alpha Centauri. Human beings, at another star, for the first time. The meaning of that moment would not be reducible to the scientific data collected, though that data would be extraordinary. The meaning would be something harder to name. The moment a species that had been confined to one place in the cosmos extended itself, by whatever means it finally found across the first interstellar distance, demonstrated to itself, and to whatever might be watching, that the distance between stars was not a wall but a passage, difficult, costly, long, but crossable. Every great human journey in history has had this quality. The first migrations out of Africa, the ones that carried our ancestors across land and open ocean to populate every corner of the planet, were not short or safe or comfortable. They were accomplished by people who had no maps, no certainty, no guarantee of arrival. What they had was the same thing every generation of explorers has had: enough drive to keep moving, enough ingenuity to solve the problems that arose, and enough willingness to accept the cost of going. Interstellar travel is that drive at cosmic scale. The same impulse, the same courage, the same acceptance of cost, scaled up from a valley or an ocean to the space between stars. Pause here for just a moment. We have travelled a long way together in this story, from the simple, almost brutal fact of 4 light years and the word nearest, all the way to the question of whether there is life at a world we cannot yet visit. You stayed for all of it. You let the numbers land. You followed the physics and the human cost and the philosophy to their conclusions without flinching away. That is not a small thing, and it deserves to be acknowledged between us. What you carry now is not just information. It is the honest weight of one of the largest questions our species currently holds. And that weight is not a burden. It is, in the truest sense, the feeling of being a thinking creature in a vast universe, which is exactly what you are. Here is the truth that this entire journey has been building toward, stated simply. The nearest stars are within reach. Not physically, not yet, but conceptually. We know where they are. We have identified their planets. We have measured those planets' masses and orbits. We have modelled their atmospheres. We have proposed credible propulsion systems that could send a probe to the nearest one within 20 years, if the engineering can be completed. We have the mathematics of warp geometry, the physics of gravitational slingshots, the biology of closed ecosystems, the psychology of long-duration isolation. We have thought about this with extraordinary seriousness. The nearest stars are, in the deepest sense, within the reach of human knowledge. They are not yet within the reach of human capability. That is a different thing. And the gap between what we know and what we can do is the gap that defines where we are right now. A species that has reached the edge of its own solar system by machine, that has never sent a human being beyond the moon, still in the early chapters of the technology the stars require. The honest restatement of this journey's central truth is not that the goal is impossible. The honest restatement is that we are early, not failed, early. The same way that 1903 was early for powered flight, the same way that 1969 was early for space exploration. Early means the hardest conceptual work is done, the proving that it is not in principle impossible. What remains is the long work of making it possible in practice. No one alive today knows what technology will look like in 100 years, or 300, or 1,000. What we know is that the problem is real, the destination is real, and the drive to go is as old as our species. Those 3 things together have, historically, been enough. People sometimes ask why we bother looking at the stars at all. Why spend the resources and intellectual energy on questions that may not be answered for centuries? The most honest answer is this. We look outward because we are the kind of thing that does. The human mind, faced with a horizon, instinctively asks what lies beyond it. Faced with a distance, asks how it might be crossed. Faced with a question about whether we are alone in the universe, finds the silence intolerable and designs experiments to break it. This is not merely a rational calculation. It is a deeper drive than rationality. One that is, as far as we can tell from the fossil record and the archaeological record, inseparable from what we are. But there is a rational argument too. The universe is old. Our species is young. The sun will last for roughly 5 billion more years before it changes in ways that will make Earth uninhabitable. An almost incomprehensible duration, far more than humanity needs to solve the problem of interstellar travel, if it survives long enough to do so. And survival, in the very long run, likely depends on becoming a civilization that is not confined to a single world. Moving outward to other planets, eventually to other star systems, is the only strategy known to physics that genuinely distributes the risk of extinction across multiple locations. A species on one world is a single point of failure. a species on 10 worlds is not. The journey to Alpha Centauri is not exploration for its own sake alone. At the deepest level, it is the beginning of a survival strategy. The most ambitious, most difficult, most human survival strategy anyone has ever proposed. The light from Proxima Centauri that reaches Earth tonight left that star more than 4 years ago. When that light began its journey, the planet we now call Proxima b was completing orbit after orbit in its permanent 11-day year, in perpetual half-light, circling a dim red fire. And the photon that would eventually arrive here was already crossing the void, indifferent to anyone watching. For most of human history, that light arrived without anyone knowing what it was. It joined the sky, unnamed, part of a background of stars that people looked at for guidance and beauty and wonder, without knowing that the nearest one was invisible, or that it had planets, or that one of those planets might hold the answer to the oldest question our species has ever asked. We know now. We have a name for the nearest fire. We have coordinates for the worlds that circle it. We understand in honest and specific detail what crossing to it would require. That understanding was not given to us. We built it, instrument by instrument, equation by equation, mission by mission, generation by generation. The knowledge we carry is earned, and the word nearest, which began this entire journey as a Latin adjective astronomers chose for its precision, has become something else by the end. Not just a positional description, a moral weight, a reminder that proximity and reachability are not the same thing, that the nearest fire in the sky is for now still out of reach. But it was not always even known, and what is known can in time be reached. We began with a name, Proxima, nearest. Not a poetic choice, just the most honest word available for the fire burning at the edge of our cosmic backyard. We end with a different understanding of that word. Nearest does not mean close. It means only less far than everything else. In a universe of almost incomprehensible distances, the nearest star is still 4 light-years away. The nearest fire still asks, honestly and without apology, whether we are capable of becoming the kind of thing that can reach it. That question is not a reproach. The universe does not judge. The stars burn whether or not we arrive. The question is ours, and the fact that we are asking it, carefully seriously with all the science we can bring to bear, says something about us. Something that, quietly, matters. We are not there yet, but we are looking.